All right, in this video, I'm going to be looking at two definitions for work. So we're going to be thinking about work in a couple different ways. Now, what we talked about in the last video, the initial definition for work is that if you apply a force that's parallel to the displacement of an object, then work is done. Specifically, if you push on something in the direction that it's moving, then you increase the amount of energy that it has. So when you do this, the energy of the object is increased. So if work causes the energy to be increased, instead of thinking of it as the thing that caused the work, the force acting through a distance, we can think of it as what the result of that work having been done is. So if work caused an increase in energy, then we can say work is the change in energy of the object. So a force acting through a displacement causes work, and the result of that work is a change in energy. Either way, we can say work is the change in energy, or it's the force times displacement. What I'm going to do now is I'm going to do two physics problems. They're actually identical problems, but we're going to see how we can calculate work by looking at the force or by looking at the resulting energies. A box, 2 kilograms, is pushed with a force of 4.5 newtons for 2 meters across a frictionless flat surface. Determine the work that can be done. The box starts from rest. Find the final velocity of the box. So, first of all, we have a force of 4.5 newtons, which is acting through a distance of 2 meters. We don't have any direction for this force, so what we're going to assume is that the force is pushing directly on the side of the box. And so we're going to assume that all of that force is parallel to that displacement. So the work then is the force times the distance, or 4.5 newtons, times the 2 meters that it acts through, which works out to 9 Newton meters, or 9 joules. If this work is realized as a change in energy, we assume it starts from rest, which means the initial energy is 0. Then the work done is going to be equal to, is being realized as kinetic energy, and so we can use it to find the final velocity of the box. The work done is 9 joules, and if it's becoming kinetic energy, then we can say that's equal to 1/2 times the mass velocity squared. 9 joules equals 1/2. The mass of this block was 2 kilograms, v squared. So v works out to be 3 meters per second. So here we looked at a force in a displacement causing work, and as a result, looked at that work to see how much energy the block had, and if that energy was kinetic energy, how much velocity that block had, or box had. We're going to do that exact same problem, but this time we're going to do it in the opposite order. A box is pushed with an unknown force of 2 meters, or for 2 meters, across a flat, frictionless surface. The box starts at rest and has a velocity of 3 meters per second. Determine the work done on the box. Determine the unknown force. So this time, and we don't know the force, so we're going to view work as the change in energy. It says the block starts from rest, so we're going to assume the initial energy is 0, and goes up to 3 meters per second, so in the final situation, it's going to have some kinetic energy. 2 kilogram box, final velocity of 3 meters per second, so I get 9 joules of work. So here, instead of viewing work as the force times displacement, I view it as the change in energy, but since we're dealing with the same change in energy, we get the same amount of work. Now, using that, it says determine the unknown force on the block. Well, if work is equal to force times displacement, this time my work is 9 joules, My force is unknown, and my displacement is 2 meters. So my resulting force must be 4.5 newtons. So you can see sometimes, depending on what it is that you know about the situation, it's useful to start with the definition of work as the force and the displacement, and sometimes it's useful instead to start with the definition of work as the change in energy.